Hello and welcome back to a little bit of chemistry practice. Today we're going to talk about acids and bases, and we're going to talk about a special type of reaction called a neutralization reaction. A neutralization reaction is when you start with an acid or a base and then you add the opposite. Like to an acid you would add a base, and to a base you would add an acid until the pH is around 7, which is neutral. Now that I've said that, let's actually look at an example so it makes sense. Let's say in my Erlenmeyer flask down here, I have a very strong acid, hydrochloric acid, and it's aqueous. Now I want to neutralize this. I want to take it from, say, a pH of 1, and I want to change it to a pH of 7, which would be neutral. Remember, water is neutral at 7, and remember that strong acids have a low pH, and anything over 7 up to about 14 is a base. So I'm going to add in a base. Let's just say I have sodium hydroxide, aqueous. I will put my sodium hydroxide in this up here, which is called a burette. And then I will turn this little lever, which is called a stopcock, and I will drip it into the acid until it is neutral. Okay. When we look at this neutralization reaction, what happens is the anion of the acid will combine with the cation of the base. Remember, these are all floating around in solution. So we always write the cation first. This will make sodium chloride. And over here, this will make water. So on a quiz or a test, if it says what are the products of a neutralization reaction, the answer is a salt. It could be sodium chloride or some other type of salt. Remember, ionic compounds are all salts. It's just a fancy way of saying it. And water. The salt that is made depends on the acid and the bases that are being used. Also, if you notice, this is something called a double displacement reaction, which we've talked about before. It's just a special type of double displacement reaction. Okay. One more thing. Before we put the base into the acid, we put a few drops of something called an indicator. An indicator is a substance that will change color when its pH changes. So, a common indicator is phenolphthalein. Phenolphthalein. Yes, this is sort of silent. So, phenolphthalein. You put a few drops of this in the acid. When it is in acid, it is colorless. And then I keep on dripping the base into here. When it becomes 7, the color should change to pink, and that is when I end the titration. So indicators are substances that we use to look at the pH of solutions. Other common indicators that you've probably heard of are litmus paper, which will change color depending on if they're in a base or an acid. So some more common questions on tests. Okay, right here we look at some titration curves. We're not going to do much with these right at the moment, maybe later. But I wanted you to look at these because these sometimes are on quizzes and tests. Notice this here would be a titration that is starting with an acid. And the pH is low. As you add more base, the pH goes up because it's changing to neutral. This over here would be a base. So in this Erlenmeyer flask, you could start with the acid or the base. In here, you could put the acid or the base. It just depends on what you want to do. Okay. Now that we've said all that, let's go ahead and look at a couple of questions in a specific equation that I want to go over. This would be a type of problem you would see on a quiz or a test or a worksheet. In fact, this is from a worksheet that you did in class. What volume of a 0.5 molar sulfuric acid is needed to react completely with 15 milliliters of 3.5 molar of potassium hydroxide? Also, write the chemical equation for this formula. Okay, when you're first looking at this, you are thinking that is a daunting task. I have to know how to write the acid and the base from memory. I have to write the neutralization equation. I have to balance it before I can really even answer this. So there's several ways to answer this question. Let's do two different methods. First of all, let's write the equation. I have sulfuric acid, H2SO4. It's reacting with potassium hydroxide. Keep in mind your anions and cations. OH is a -1, potassium is a +1, so that's how we write that. What is this going to make again? Well, this cation will combine with this anion. So now we have potassium sulfate. But some of you smart students are probably already saying, you're messing up. Wait a minute, this potassium is a +1. Okay? It has a +1 charge. This whole anion, this polyatomic anion, is a 2-. So I'm going to need 2 of these. Remember that crisscross method we learned? Now it's coming back into play. Plus water. Okay, now we have to balance this thing. Well, the first problem is we only have 1 potassium, so let's put 2. But now I have 4 hydrogens over here. 1, 2, 3, 4. So I'm going to have 4 hydrogens over here. Now I have 2 oxygens. I have 2 oxygens. I have 1 SO4, 1 SO4. So that balances. Okay, great. So the first way we could do this is simply by dimensional analysis. Now, one thing to keep in mind, when this neutralizes, the amount of moles of hydroxide have to equal the amount of moles of acid. That's what's going to make it neutral. Okay, so the moles are going to be equal. So we can use that idea to now do dimensional analysis and stoichiometry. So the very first thing I could do is look at this and say, okay, I have 15 milliliters of potassium hydroxide. How many moles is 15 milliliters of this stuff? If I'm going to use 15 milliliters of potassium hydroxide, I could figure out how many moles I need, then I could figure out how many moles of this stuff I need. So I can do that by using molarity. Remember, molarity is a ratio. That's a big M. It equals moles of solute per liter of solution. So I know in 1 liter of solution, this stuff has 3.5 moles. He gives it to me right there. That's 3.5 moles per liter. Or I could then flip it upside down for this ratio. Now I can almost use this. My problem here is I have milliliters and here I have liters. To change milliliters into liters, I move the decimal place 3 to the left. 1, 2, 3. So it's 0.015 liters. 0.015 liters. Now this will cancel. Okay. All right, now I need to look at the ratio in my balanced equation. I have a 1 here, and I have a 2 here. So remember, I should have put, this is my potassium hydroxide. So for every 2 moles of potassium hydroxide, I'm going to balance it with 1 of sulfuric acid. Now if I do this little math here, I should get moles of sulfuric acid. If I do that math, I will get 0.0262 moles of sulfuric acid. Wow. But now I need to figure out volume. I just have moles. How do I do that? Remember, molarity equals moles over liters. Liters is volume. So I don't know the volume. This is a big question mark. Do I know the moles? Yes, it's 0.0262. 0.0262. Do I know the molarity? Yes, 0.50. So 0.50 equals 0.0262 over x. Now, I just do a little bit of algebra, and I do 0.0262 divided by 0.50 to find x. And when I do all that, I'm going to get my answer of around 52 milliliters. Well, by the way, the answer is going to be in liters, and I could convert it back to milliliters. All right, wow. So that seems like a lot to do. Is there any easier way we could figure this out? Well, as it turns out, they have a nice little equation in the packet that was given in class. That little equation says molarity 1 times volume 1, okay, times something called the number of hydronium ions equals molarity 2 volume 2 times the hydrogen ions. Well, could this be easier? Well, let me see here. So molarity 1 is, I could just put 3.5 moles right here. Volume 1, I could just keep this in milliliters. That's 15 milliliters. All right. Now, what does this mean? Well, that means right here, if I look at this potassium hydroxide, there's really only one hydrogen ion in here. So I'm just going to put 1 equals molarity 2, 0.50, times volume 2, which I don't know. Remember, I need that. I'm just going to put X, times the hydrogen ions. Okay, so this one's a little bit weird. This is sulfuric acid. If I look at this, this will dissociate. I'm going to get 2 hydrogen ions out of this. I'll get 2 of these. So I have to put 2 right here. So now, if I do this math, I'm going to end up with basically X equals 52.5 milliliters. Wow. Okay, that seemed way easier than the stoichiometry that I was doing to begin with. And you're absolutely right. That's why it's in the packet. But I just wanted you to know that there are other ways of doing this equation, and sometimes it really depends on what makes the most sense to you. Sometimes equations are useful, but we have to know where they come from and why they work. Okay, now here's one other way I have seen this that to me makes actually the most sense. Okay, I'm going to take this 2 out right here. I'll just erase the whole thing. I've seen molarity 1, volume 1, divided by the mole ratio of 1 equals molarity 2, volume 2, divided by the mole ratio of 2. So in this instance, I look at the balanced equation, H2SO4. Okay, let me add this in. I have 0.50 moles of sulfuric acid. I'll just put that right here. 0.50 moles. I don't know the volume yet again, right? Just like before. Over here, I have 3.5 times 15.0. Now, I look up here and I realize, wait a minute, this is a 1. So underneath here I put a 1. For the potassium hydroxide, I have a 2. So underneath that side of the equation, I put a 2. Okay, now I do a little bit of math. 3.5 times 15.0 equals, divided by 2, equals 26.25 over here. Running out of space. 26.25 equals 0.50x. So x equals 26.25 divided by 0.50. And I get 52.5 milliliters. So, I'm sorry that took so long, but basically I've just shown you 3 ways to solve this. Personally, I would use this method. For me, this makes more sense because underneath each side, I'm putting the mole ratio from the balanced equation rather than counting up hydrogen ions. But maybe the hydrogen ion way is easier for some people. I don't know. Let's go ahead and look at another example. A student spills about 30 milliliters of a 6 molar hydrochloric acid solution, this seems to be misspelled, on the floor. What volume of a 3 molar solution of sodium hydroxide would be needed to neutralize the acid? Well, this is the same thing we just did. First of all, I could write an equation. All right, we have hydrochloric acid plus sodium hydroxide equals, remember this is going to be a salt. Put the cation first, sodium chloride. Make sure that these balance out. This is a -1 charge, that's a +1, so that does balance. I don't have to do a crisscross. Plus water. Now make sure that this whole thing is balanced, and it is. This one's pretty simple. Okay, well, that just tells us there's a 1-to-1 ratio right here. 1-to-1. That makes it easier. Now let's use our equation. Molarity 1, volume 1. I'm going to go with the mole number under here. Equals molarity 2, volume 2, mole number. Well, the moles are 1. So we really don't even have to do the bottom. Okay. So I have 30 milliliters. 30 milliliters. The molarity, our concentration is 6.0, equals 3.0 molarity. And I don't know the volume. Let's just say X. So X is going to equal 180 milliliters over 3.0, which is going to equal 60 milliliters. Okay. Now I should point out one thing. This is a strong acid being neutralized by a strong base. If I look in this problem here, this is a strong acid and a pretty strong base. So in this class, we don't need to get into strong acid, weak base, or strong base, weak acid, which are actually going to throw a little bit of a wrench into our equations. But this is the last example. We made it. So it takes 38 milliliters of a 0.75 molar sodium hydroxide solution to completely neutralize 155 milliliters of a sulfuric acid solution. What is the concentration? Notice this is also a strong acid and a strong base, but sulfuric acid, what do we have? H2SO4 plus NaOH equals, bam. Now, this is a +1. This is a -2. So I'm going to need 2 of these, Na2, to balance out that SO4 plus H2O. But now I have to balance this. Okay. If I notice right now, I have 2 sodiums, whereas here I only have 1. So I'm going to have to put 2 right here. Now I have 1, 2, 3, 4 hydroxides. Here I only have 2. So 2 H2O, 2 oxygens, and 2 oxygens. Now that is balanced. Okay, so I will use my equation. Molar 1, volume 1 equals molar 2, volume 2. It takes 38 milliliters of sodium hydroxide. Okay, So let's put 0.75, that's the molarity, times 38 milliliters over 2, because that is the mole ratio in front of it, equals molarity 2. Actually, I don't know the second molarity. Concentration, that means molarity. Do not forget that. It's just another way of saying it. But I do have my volume, 155 milliliters. So this M2 is just there, times 155 milliliters. And if I look at the mole ratio, it's a 1. Okay. So I go ahead and do that math. 0.75 times 38 divided by 2 equals 14.25. Equals basically M2 155. All right, so M2 equals 14.25 divided by 155. Which is going to give me 0.091 molarity. So that is my concentration, 0.091 moles per liter. Okay, and I think we're good. On a test or quiz at this level, you're really only going to have to do a few of those basic calculations. You might have to identify some of these objects used in the titration neutralization, and you might have to do some calculations with these graphs, which we'll work with later. So I hope that helped you out. As usual, if you have any questions, let me know.